All right, thank you, Raphael, and thank you for the opportunity to talk about my work. I swear I tried to choose colors for this Beamer presentation that didn't look like the standard colors, but I think the projector is conspiring to make it look like the standard Beamer colors. So I apologize. Okay, so usually I think these objects are called vector-valued modular forms. I tend to dislike that name because vector-valued is very general. So in the title I'm trying to be more precise what these vectors are. But I'm speaking about modular forms that take values in these vectors, vector spaces that are additionally endowed with the representation, the Weil representation. Okay, so how does this come about? Consider you can take this very simple, probably one of the most basic theta functions. It's a Q series where you stick like a single variable quadratic form and the exponent q to the n squared. And you view it as just as a power series in ZQ. And you can generalize this. I mean, I just picked this example, but you can stick any quadratic form up here, take many variables. You can do all sorts of things to get what are called theta functions and lattices. And they're interesting because their coefficients encode several important arithmetic properties, combinatorial properties of your lattices of your quadratic forms. But let's stick to this simpler case. Now, what happens with this power series? I claim that it's special because what happens is that when you plug in q equals to e to the 2 pi tau, where tau is a variable in the upper half plane, then it's easy to see that you get an analytic function of the upper half plane. And moreover, you get this sort of magic transformation formula under linear fraction. There's some type of linear fractional transformations in gamma naught of 4. And this transformation formula, what you get like a half integral way automorphic factor coming out of it, and some kind of fourth root of unity depending on c and d that you can write out explicitly. It just doesn't play any role in this talk, so don't need to worry about that for now. And that's sort of surprising because you look at this Q series, it's very simple. You don't think it's going to have like anything special about it, but when you do consider it as an analytic function, it has this functional equation. Now, if you want to look at these guys from like an algebraic point of view, which is what I like to do, then it seems quite arbitrary to just stick in q equals e to the 2 pi tau in here and considering it as an analytic function of tau. So what I'm asking today is there a way to make sense of this property of being a modular form of weight 1/2 directly from the power series? Okay, so here's the question that I'm asking today. How do we express the fact that this power series that we wrote down is modular, but without having to consider it as an analytic function, right? Because we don't even have a way of expressing it unless we consider it as an analytic function of tau. More generally, I'm going to consider it just turns out to be easier to consider a whole family of single variable theta functions where you put a quadratic form n squared over 2m in the exponent, and you don't sum over all the integers, you just sum over the ones that are congruent to certain congruence classes modulo m. Okay, and m throughout the whole talk is going to be a positive even integer. Okay, so you take this power series, and the question I would like to ask is, how do we express the fact that these guys are modular forms of half integral weight? How do we, without, just as power series of C, without having to consider them as analytic functions, without having to stick in q equals c to the 2 pi tau and consider them as analytic functions? Now, what makes you think that, I mean, what makes us think that you can actually do this? So after all, you could have the functional equation is a purely analytic fact. It just depends on viewing your power series as a analytic function. It might as well just be like that. But there's like a whole maybe philosophy behind this question, which comes from what happens for classical, like integral weight modular forms. Right, if I give you a modular form of integral weight, you can, as an analytic function, is this holomorphic function in the upper half plane that satisfies this functional equation with respect to SL2Z, right? And for these types of modular forms of integral weight, we do have a beautiful algebraic geometric theory, which is that we view them as sections of the Hodge bundle, or tensor powers of the Hodge bundle, here, over the moduli stack of elliptic curves, which I denote by M1. Right? We have this algebraic incarnation, and by that I mean that if you do this construction over an analytic base, for elliptic curves over an analytic base, you recover exactly this definition. So that's, in this sense, they form an algebraic analog of classical modular forms of integral weight. Now, what happens is that you can look at Q expansions of modular forms of integral weight. Analytically, you get from the functional equation here that they're translation invariant, so they have a Fourier expansion with respect to e to the 2 pi I tau, and we call that a Fourier expansion at infinity. Okay, and it's purely analytic notion. But then there's also an algebro-geometric notion of Q expansions. That comes from pulling back these sections over the Tate curve. So that there's a special elliptic curve called the Tate curve over this ring of Laurent series. And that's classified by a map to the moduli stack. When we pull it back, it turns out that the Hodge bundle is trivial and can be, moreover, it's got a canonical generator that it's called omega can. And what you get is, in this way, you can canonically associate to a modular form a Laurent series in this ring. And that is the Q expansion of your modular form. And of course, there is work in showing that, if you define modular forms algebraically, you get exactly the same Q series. But we won't get into that. But you see, from this point of view, now what you can do, if I give you a power series, then at least philosophically, at least there's a way of saying when this power series satisfies a functional equation of a modular form of integral weight. And the answer is that you just require this power series to be in the image of the Q expansion map. Right? So in this way, I can just say, without having to view your Q expansion as an analytic function, you can just say, OK, well, a power series is a modular form, behaves like a modular form of integral weight if it comes from an algebraic-geometric, if it is the Q expansion of an algebro-geometric modular form of integral weight K. Right? It kind of encodes, this fact of being in the image of the Q expansion map encodes the fact that this power series is special in the sense that it should satisfy a certain functional equation when you consider it as an analytic function. But you don't have to mention at no point in here the analytic function associated to this power series. So now, using this as using this theory of algebraic modular forms of integral weight, what I would like to do is to do the same for this kind of theta series. And at least take my word for that. You don't have to really restrict to these types of theta series. I can actually do the same for theta functions attached to any positive definite lattice. But for this talk, we'll just restrict to this kind of simpler single variable theta functions, theta constants. OK, so can we make a similar definition? If you give a power series of a theta function, how can I express the fact that they're modular forms without having to consider them as analytic functions? And perhaps more seriously underlying this question is perhaps like a more philosophical motivation, but more seriously, can we actually construct an algebraic-geometric theory of modular forms of half-integral weight or theta functions, just like we do for modular forms of integral weight? Can we do that? OK, so here's more serious motivations if you want. If you have this picture for modular forms of integral weight that it's well known, certainly to this audience, that starting from this algebraic geometric theory of modular forms of integral weight. Oh, OK, well, we can. I don't think those are. Oh, half integral weight. Half integral weight. It's of half integral. It's of half integral weight. Yeah, but are they interesting? Right? I'll get to it. Hopefully it will become clear. So what I was saying is that this algebraic theory of integral weight modular forms is not just like a philosophical device to pick out power series, but really, in a way, it's a cornerstone for the whole theory of motives attached to modular forms of integral weight and L functions. So given that, can you using, if I give you an algebraic theory of modular forms of half integral weight, ictor-valued modular forms, can you, and there is some, at least in the complex analytic case, there is a well-known theory of Ecke operators for these objects. Can you construct motives attached to these objects? Or maybe they're not, perhaps motives here is not the right word because, it's a very strict requirement what a motive should be. But objects like, that appear in the cohomology of certain modular curves and certain relations, you can make Galois representations or crystalline crystals or de Rham modules, things like that. Can we do it for half integral weight modular forms once an algebraic-geometric theory is set out, it's laid out? So that's perhaps like a more serious motivation behind my work. Okay, so hopefully now we're on the same page that this is somewhat of an interesting something that's worth pursuing. I mean, the L functions of theta functions are quite interesting if you think about where they come from. Okay, so how would you go about creating an algebraic-geometric theory of theta functions? So if you think about, if you use your model to be classical integral weight modular forms, and you try to understand what these things have in common with theta functions, to me the first thing that came to mind was that, well, classical modular forms, they're built out of embedding an elliptic curve into P2. And you use, at least for level 1, you use your Eisenstein series and you build a whole theory out of that. Theta functions, at least the ones I've wrote down, they come out as coefficients of embeddings of elliptic curves into higher projective space. So the first thing that comes to mind is like, well, what about, let's try and Google equations defining elliptic curves. And that's kind of doesn't lead you anywhere because usually you use the Weierstrass model anyway. But when you think about higher dimensional abelian varieties, and what theta functions are used for are to embed these abelian varieties into projective space. So the first thing that you try and look up is one equation defining abelian varieties, and sure enough, you get this series of papers by Mumford from 1966-67, where he completely addresses the question of how to give like a whole algebraic theory of how to embed abelian varieties in projective space in certain canonical ways. And you take the first paper and he says, my aim is to set up a purely algebraic theory of theta functions. And you think you're happy that this is the paper that you need in order to set up like an algebraic geometric theory of modular forms of half integral weight. And what he means by this, I've read these papers a lot, and what he means by this is really has to do with embedding abelian varieties into projective space. That's what he's interested in. What he doesn't address, as Mumford, is how do you account for these transformation laws of theta functions? How do you account for the dependency on tau or t in the Siegel-Apparatus space? How do you account for that in a geometric way? And in fact, if you scroll down a couple of lines, Mumford says there are several interesting topics which have not gone into this paper, but which can be investigated in the same spirit. For example, and he gives you a list of very interesting topics. And he says, a discussion of the transformation theory of theta functions. Okay, that's something that, believe me, in none of those 3 papers that I know by heart, he does that. He addresses this, the transformation theory of theta functions, with respect to tau, of course. I'm talking about if you view a theta function in terms of 2 variables, we're only talking about tau here, the variable in the Apparatus plane or in the Siegel space. Okay, so that's what we have to do. Now, just a quick review of Mumford's theory of algebraic theta functions, so that I want to be clear what I borrowed from him and what's really new here. Now, here's the general setup. You take an elliptic curve over a scheme, and I'm always going to invert. I take m a positive integer, positive even integer. It's not going to be 0. Sorry about that. We're not interested in the case equals 0. It's done. And I'm always, the base is always going to be, m is always going to be invertible in the base. And I take this line bundle, this invertible sheaf, over my elliptic curve. And it's essentially this sheaf of functions that have a pole order worst m along the identity section. And then we normalize it so that when you pull back along the identity, you get the structure sheaf of OS, you get constants. Okay, so this is just a normalization factor to normalize your invertible sheaf. Okay, so that's the notation I'll be using. Now, as I said, it's normalized. So when you pull back along the identity, you get an isomorphism, so you can evaluate sections. You can take a section and then speak about its value along the identity. And okay, so now let's form a locally free sheaf of rank m over my moduli stack that corresponds to a rule that to each elliptic curve associates the push forward of this invertible sheaf. This is going to be a locally free sheaf of rank m, Riemann-Roch, or whichever way you want to see it. And now we have this rule that associates to every elliptic curve over a scheme this evaluation map into the dual of this sheaf that I call Jm. I call it Jm because it's closely related to, over the complex analytic, over the analytic base, it's closely related to Jacobi forms. So that's why I use Jm. But anyway, this evaluation map gives you an analog of what should be called theta constants. Okay, so it gives you a vector. You get a vector in this dual vector bundle, vector with m components. And if you really go through all the conceptually, and you have to go through some calculations, but that's all been done, you get a complete algebraic analog of theta functions. And that's really what, this is what Mumford's theory is entirely concerned about, studying this kind of vector and trying to write it down canonically, and there's group actions in here that kind of cuts it down, cuts the sheaf down in different pieces, and it's a very beautiful theory that sort of inspired everything that I'm going to talk about today. Exactly. Yeah, it's the variable, the complex variable. Right. Okay. So, right. So what we have to address is, you see from here, from this definition, it's very beautiful, but you can't see the transformation law, the dependency on tau. You can't see it from here. Even if you write down complex analytic, you're going to get some kind of Jacobi forms here, and right. But well, I refuse to say it because it's an analytic.
Well, it's just what you're trying to do.
Exactly. It's exactly what it's precisely what I'm trying to avoid. Right. Exactly. Okay. So before I start, there is a convenient way of writing down the transformation laws of theta functions in the complex analytic world, and this is to say you take this theta null vector. So you put all the theta functions that I listed before, this theta mu, theta m sub mu. You put it in a vector of m components, and it really corresponds to the algebra-geometric construction that I did in the previous slide. Okay.
I mean that you write it as a number.
Right, to write this. Right, there is the whole theory of like theta structures that you have to use, the Mumford's theta structures over the take curve that you can do. And ideally, we'll talk about that if I had another couple of hours, but I'll try to gloss over that detail. Okay, so while the transformation law in this case takes this form, so in this vector can be compactly written as a transformation law under my laser is not working anymore. It's a transformation law with respect to a double cover of SL2Z, the metaplectic group. And you see you get like a half integral wave automorphic factor, like this phi, which is squared is theta plus d, plus a representation, which is called rho m. And that rho m is well known. There's very well-known formulas for it. It's the Weil representation. So in terms of this Weil representation, you can write down precisely what the transformation law of theta functions is, and it's very compact, and efficient way of doing it. So that's what we're going to try to replicate. We're going to try and construct vectors, and we're going to try to understand what it means for this vector to behave in this way, in a completely algebraic geometric fashion. Okay, so here's again the complex analytic definition. So forget about theta functions now. we're gonna abstract out the transformation law of theta functions, and we're gonna define vector value functions. So from the upper half plane into this group ring that, although we just view it as a complex vector space with a canonical basis of delta functions. So a vector value modular form is a holomorphic function. It takes values in this group ring, and it transforms according to the transformation law of theta functions. So the Weil representation acts on this group ring, and I should stop pointing with this. It's becoming useless. Right, so the SL2R is a unique non-trivial double cover, and you take the preimage of SL2Z into that, right? And you can write a model for it, Shimura style, as a matrix, and a half integral wave automorphic factor phi. So phi squared would be theta plus d. Okay, so this is a definition that goes back perhaps to the Eichler-Zagier and later on by Borchardt. That's really what we're trying to replicate and what we call vector value modular. This is what they're called vector value modular forms. Okay, here's a little fact. Perhaps adds some special meaning to why we consider half integral weight. The fact that there are no interesting vector value modular forms of integral weight. Okay, you just play around with this. It's kind of like the same fact that you don't have level 1 modular forms of odd weight. From the transformation law, you're going to get something like negative f equals f. You don't get anything. So that's why we have to take half integral weight. Otherwise, we're not going to get a meaningful theory here. Okay, so here's a first sort of geometric point of view on this subject, and the way I want to view vector value modular forms is to view them as sections of a vector bundle, and I'm going to tell you exactly what these terms are: Wm and omega k over 2. Although from the letters it should give you a clue. But so I first formed this quotient, this orbifold of the metaplectic group. So metaplectic group acts on the upper half plane through its quotient SL2Z. So when I write this double bar, I really mean the orbifold. So I also keep track of the stabilizers, which are all finite. You're going to get generic stabilizer is going to be order 4 as opposed to order 2, which is what you usually take. Okay, and what are these two? I have a line bundle, omega to the k over 2, which must correspond to this cocycle. So it's a cocycle with of MP2Z, one cocycle, and I map phi, the half integral automorphic factor, to phi to the k. That's a one cocycle of MP2Z with values in holomorphic functions on H. So essentially by definition, or well, not really by definition, but that should correspond to a line bundle over my quotient, which I call a metaplectic orbifold, just a quotient of the metaplectic group, quotient of the upper plane by the non-trivial double cover of SL2Z.
So you have gamma square root CZ plus D by 2 phi.
Right, phi is a square root of theta plus D. Yeah, or CZ plus D. Yeah, okay, so that's the easy part. And now Wm is going to be, for this talk, you could just take a vector bundle, but in fact you get more. It's a local system of rank M. And it's the one corresponding to the Weil representation. So essentially, that's the definition. You consider local system over this metaplectic orbifold is exactly like representations of MP2Z. You can view MP2Z as the fundamental group of your orbifold, and that's a representation of the fundamental group. That's what Wm is, should correspond. So this way, I've rewritten the definition. I haven't done much. Just rewritten the definition in some geometric terms that might help us do an algebraic geometric analog. Okay, so here's my to-do list. I need to give you an algebraic analog of this metaplectic orbifold. Okay, so it's going to have to be some kind of stack. And of course, I mean, the first place where you look at is the usual stack that you work with, the SL2Z modulo, or H modulo SL2Z. That's a moduli stack of elliptic curves. So what I'm going to do really is just this. When I say algebraic analog, I really should say a moduli theoretic analog. I'm going to create a moduli. I'm going to interpret this as a moduli space. That's what I'm going to do. And then over that, I'm going to construct this omega k over 2, and then I'm going to construct another stack and give you this algebraic analog of the Bell representation local system. Okay, that's the to-do list. All right, before we do that, just a little, probably not really meaningful definition. I just like using this term, so I don't have to repeat the term gerb all the time. But so I'm going to call M1 the modular stack, okay? And any gerb with band mu2 is going to be called a metaplectic stack, okay? So a mu2 gerb is something that locally looks like mu2 torsors over your stack. Okay, so essentially, by construction, these metaplectic stacks are going to be classified by two co-cycles taking values of mu2. So here's a little bit of an explanation behind the terminology, which I think I owe you. Over the analytic base, the modular stack of elliptic curves is just the usual quotient, SL2Z by H. Now, the H2 is going to be equal to plus or minus 1. So you're only going to have two metaplectic stacks over C, over an analytic base. You're going to have a non-trivial one, which is our quotient that we're interested in. And then you're going to have like a trivial quotient. So that's why I try to call it. But perhaps a metaplectic stack should be non-trivial mu2 gerb over the modular stack, if you want to be more precise. And here's a little notation. I sort of borrowed also some ideas from the metaplectic correction method in geometric quantization theory. If you're familiar with that, you'll recognize some of the same techniques. Okay, so what is this? Remember, we have to start by constructing these metaplectic stacks, right? So let's do it. It's going to be some kind of moduli space of an elliptic curve with some other structure on it. And let's take my base. I'm going to always invert M. M is even, so I'm always inverting 2 as well. Well, the topology, if you want, you can take the Ital topology underlying all these constructions. Now, what I call M1F is going to be the category of pairs of an elliptic curve over a scheme and a quadratic form on it. Okay, I need this single variable quadratic form. So in this geometric terms, a single variable quadratic form should be an invertible sheaf such that it squares the Hodge bundle. Okay, and also sometimes I'm going to be, maybe I might be a little sloppy and drop the I, but the I is crucial to get this definition to work. So the I is just an isomorphism in this square and the Hodge bundle. Okay. Now you can show that it's a Deligne-Mumford stack, and moreover, it's a mu2 gerb. The automorphisms of this pair are just at least over a geometric point. It's just going to be plus or minus. They're going to be the automorphisms of a single variable quadratic form is always going to be mu2 at least over a geometric point. So you get automatically, well, you have to do some work, but it's essentially the simplest example of a mu2 gerb you could come up with. If you try to think about what mu2 gerbs should look like, that probably would be the first thing that you try to write down. Okay. Moreover, what's special about this metaplectic stack is that I can construct a sheaf on it, invertible sheaf, omega to the 1F. Okay, just by this assignment, I'm going to assign to a pair of an elliptic curve in a quadratic form the sections of the quadratic form over the base. And that sheaf is omega 1F because when I pull back, essentially by construction, when I pull back omega to M1F, the Hodge bundle over M1F, I'm going to get that it acquires a square root. That's not something you can do over M1. Okay, that's probably why I should probably explain why I do this construction. If you try to find a square root of omega over M1, you find that you can't do it. It generates the Picard group, which is mod 12C. So you can't do it. You have to pass over this mu2 gerb and then find a square root there. That's the meaning behind. That's why I have to construct this M1F. Essentially, it's the stack that's been designed, has been built on to have a square root of omega. This is the Hodge bundle. Okay, so that was first on my list. construct like omega 1f and take tensor powers of that. That would be omega to the k over 2.
So, repeat my question. Why don't you take it also?
I think you can, but then the sections wouldn't be that interesting, I don't think. I don't know. Are you sure? Maybe we can look into that, but. Yeah, I have a bit of a philosophical thought about that too, but we'll talk about that later too. I'm sure your insights are better than mine. Okay, now let's get to the hard part and the most interesting part, which is how do we algebraize? How do we make an algebraic-geometric analog of this Weil representation of rank 1 quadratic forms? Okay, so remember we have this invertible sheaf over an elliptic curve. Okay, I repeat the definition. It's just a function with poles along that entity of order of worst m, normalized. Now, there's this construction due to Mumford. It's called a theta group by Mumford. More general constructions might be called Heisenberg group. But nevertheless, you take your, in this setting, you take your invertible sheaf Lm and you restrict to the m torsion of your elliptic curve. And what you get, you don't just get a GM torsor over EM, but you actually get a group structure. That comes from the theorem of the cube of a billion schemes. So there is a bit of work there to justify why this is a group, but nevertheless it is. It's a central extension of GM, and by our assumptions, remember M is positive and even. GM is exactly the center of this group. And you can form a commutator form of this group and will correspond to the Weil pairing. And all these facts that it's all worked out by Mumford and other people. Okay, now what happens is that if you push forward your sheaf, you actually get an irreducible representation of rank M of your Heisenberg group. And that's really the algebraic theory of theta functions. You get this Heisenberg group acting on the sheaf, and it breaks it down into line bundles, and each line bundle is going to correspond to a certain theta function. That's what I'm going to talk about next. It's exactly. So what's another way of constructing representations of the Heisenberg group is Weil's idea of using Lagrangian subgroups, or many names attached to that.
Sorry, I read in the Weil theorem first, not this.
Oh, sorry. Yeah, you can show that. You can show that the commutator pairing of this is the Weil pairing. Yeah. Yeah. Okay. But that leads me to my next point, which is how do you construct the other types of representations of this group? And that's where some of the more delicate analysis is involved. Now, we have to take into consideration the fact that the sheaf L, I haven't really talked much about it, it's more like a technical condition, but Lm is symmetric, meaning if I pull back by the inversion morphism of the elliptic curve, it's isomorphic. Lm is isomorphic to negative Lm. And that induces an involution of my Heisenberg group that lies over the inversion morphism. EM is a billion, so you get that's actually an automorphism. And this delta -1, using Mumford's notation, just lifts -1. It's that entity on GM. That's the extra structure that we're going to use. Because you need some extra structure. You'll see why. And that's really. Oh, you want to. The identity where? Where? Which? Oh, okay. Right. I could. I mean, you want in terms of. I just because I haven't really defined GL that well for you, but. The identity. Oh, I see. I think you want the identity, right? Right. Yeah, I think so. You want to be the identity of the trivialization. But I think the issue is that when you, how is that compatible with the trivialization of LM along the identity, right? That was the issue. So you wanted to.
I saw it come from the functoriality. The E1 of E2.
Well, yeah, but you have to pick because it's not quite. So LM is, you also, part of the data of LM is also trivialization along the identity section. So I'm going to have to tell you exactly how this delta 1 is compatible according to that. So that's a delicate point. I think yeah, we're going to be the identity there. Yeah. Thank you. Okay, but this extra structure, what it gives you is that, in fact, GLM is a mu2 torsor over EM. So a priori is forget the group structure, it's a GM torsor over EM, but with this extra structure, I can actually give you the structure of a mu2 torsor. I can find an isomorphism within the tensor square of that with the trivial torsor. Okay, and that's kind of important in this construction. Now, and here's a bit of I'm reworking definitions that date back to Weil or Shale. So a way to construct representations of the Heisenberg group is to take these so-called Lagrangian subgroups. So these are subgroup schemes of rank M, and when you project them onto the torsion, you're going to get a isotropic decomposition between, so the projection of script H is H, a capital H, and that decomposes, that needs to, well, they decompose EM. So that's an extra condition that I need to impose in here. And not only that, but I also require some kind of compatibility with delta -1 with my involution. And what I require is that my symmetric Lagrangian subgroup, essentially the involution acts as an involution, as the standard involution. You can prove that it's commutative, so everything. So G is not, the Heisenberg group is not going to be commutative, but a Lagrangian subgroup will be, because it's isomorphic to its image, capital H. So everything makes sense here. So I call this, so that usually the term is Lagrangian subgroup. I added this condition, symmetric. And that, if you want, if you're familiar with the Weil representation or Weil's paper on the Weil representation, is really this condition of lifting a group H in my torsion to a group in the Heisenberg group by using second-degree characters. Right, so there's a whole series of second-degree characters in the Weil paper. They're essentially exponentials of quadratic forms. And that condition of using second-degree characters really translates into requiring your Lagrangian group to be symmetric. That's kind of like a bit of a key assumption, actually. Okay, so now what do we do with this Lagrangian subgroup? I'm going to define representation. These are usually called Schrodinger representations. I'm pretty sure that Schrodinger didn't define this way. Okay, it's going to be, if you're familiar with this kind of theory, it's the same idea. I take functions on my group, which are left invariant by the action of the Lagrangian subgroup, and they also where GM, which is embedded into the Heisenberg group, kind of factors out, acts like a natural scalar multiplication. Now, there's a delicate part here, which is how do you define, okay, I've defined these objects, this Schrodinger representation. The delicate part is like, how do you actually define the morphisms between these Schrodinger representations? That's really where a lot of the work in this business with the Weil representation falls into. It's about defining the right category of morphisms. And what I notice is that if you actually take, so you can take this quotient, these are all affine schemes. So you take this quotient of the Lagrangian subgroup by the Heisenberg group, and because of the symmetric assumption that I've made, you actually get a mu2 torsor over the Cartier dual of capital H, which is the projection over the torsion. And here's my definition of a morphism of Schrodinger representations, that it should be a G modular isomorphism, so it should preserve the action of G on both Schrodinger representations. And moreover, this isomorphism should be coming from mu2 torsor isomorphism. So it's a bit of a delicate, it's a bit of a technical condition that Yeah, so this, so this, oh, sorry. So this WH is really, I could write in a different way as the push forward over H dual of that torus over there. Right, so you do get an isomorphism by functoriality. So coming from a situation like this, you do get by functoriality an isomorphism of the corresponding Schrodinger representations. But then when I'm asking extra, is there also this isomorphism respects the G action, and that's involved in cutting down. So when you do work with this distance of the Weil representation, you usually use the Stonewall-Neumann theorem to ensure this kind of isomorphism exists. But then you can only pin them down up to a scalar, or up to a scalar, or up to a constant function. In this way, if you take into account the mu2 torsor structure, you actually can pin down the isomorphism to plus or minus 1, which is a key point, because what I want is that the automorphisms of my Schrodinger representation should be plus or minus 1. It shouldn't be GM. If I compare with I don't think Weil does in that paper, but starting from that, you can. Right. Yeah. So I'm not a no, I don't know that paper as well as the Mumford paper. Let's put it that way. Okay, so the key point of this construction is that the automorphism of a Schrodinger representation is so defined, it should be defined up to plus or minus 1. Okay, so now we can put everything together. I'm going to define the category of pairs, kappa m. It's going to be a category of an elliptic curve plus a Schrodinger representation. Now that category is a mu2 gerb. Precisely, it's a mu2 gerb over m1, over the modular stack, precisely by this condition of the automorphism being defined up to plus or minus 1. So by construction, what you get is that this stack is going to be endowed with a locally free module Wm, W is for Weil, just by the usual, the most obvious rule, taking an elliptic curve and a Schrodinger representation and sending it to its sections. Okay, so now we got all, if you remember my to-do list, we got all the pieces put together. Let's make this definition. I'm going to define m is a positive even integer, k is an integer, a modular form with values in Wm value, vector value modular form, of weight k over 2. K is an integer, so you could have half integral weight. It's a global section of this sheaf, and it's over the contracted product of gerbs. So you have to get, remember kappa m and m1f, you got to combine them together, and the action of mu2 has to be diagonal. But anyway, there's this product over here is the contracted product of mu2 gerbs, form this tensor product. That's my definition of what a vector value modular form should be. Okay, so that took me about 45 minutes. So what are some theorems we can prove about this vector value modular form? Let's get to, I haven't proved anything so far. It was all constructions. So let's see what kind of properties these guys have. Now, the first is that if I just give you this definition, why are they modular, right? Something modular should be defined over M1, over the modular stack. Should be modular forms. So, okay, so well, this is to give you like kind of a picture, just, remember this is geometric definition. I just wanted to justify why it's a geometric definition, because when you go over an analytic base, your gerb kappa m, your metaplectic stack kappa m, your metaplectic stack m1 after, both going to be equivalent to this non-trivial quotient. And you have to do some calculations, but you can show essentially by construction you recover what you wanted. That omega to the k over 2 is what that cocycle, and Wm is given by the Weil representation. There's fair bit of computations here that you have to check, that I've checked. But essentially, I've constructed things in a way that you get this back. So that was the main idea. And this is working over an analytic base. So that, in that way, I call them algebraic analogs of vector valued modular forms. So now, what are some theorems? What I was hinting at before, these are actually modular. Okay, so what happens is that if you take k to be odd, then somehow this Wm has got automorphisms that are defined up to plus or minus 1, and same for omega to the k over 2, and it just turns out that they conspire so that they kind of cancel each other out, and everything descends. Even though neither of the omega to the k over 2 or the Wm is defined over the modular stack, their tensor product is. It descends. So locally free shift over Nm over M1. So you see, what I like to think about these metaplectic stacks is to be entirely auxiliary to the definition. But once you've done the construction, you can just work over M1, which is very nice, actually. Yes, I would think so, and it's kind of have to do with the fact that. Yeah, over 1 over m, right. I'm just a bit like comfortable talking about these isomorphisms because they kind of all come from the fact that there aren't that many 2 cocycles to go around. So right, but we can talk about this technical point later. But for example, if you're working with an arbitrary base, you're going to get into problems instead of z. Absolutely, because you're going to get cocycles coming from the base. Yeah, it's a bit of a delicate issue. So that's why I like to state this theorem in this way as opposed to saying that certain gerbs are isomorphic. I just like to say that this tensor product descends over M1, and that's always true over any base. Okay, and then what happens when k is even? In the integral way case, you get exactly like before. There are no non-zero vector valued modular forms, so we don't care. In the odd case, you descend to M1. In the even case, there are no interesting ones. So that's the first result that I get about this construction, which is satisfying. Perhaps justifies why we use half integral. But here is really what I consider like the fundamental theorem about this whole business, the most important result that I get. So remember that you have this J M, this sheaf of Jacobi forms, if you want, that's obtained by taking the sections of Lm over the base. Okay, these are like Mumford's algebraic. That's where Mumford's algebraic theta functions live. And now here's a non-trivial result, which is that if you take Wm and then you tensor it by omega to the negative 1/2, so negatives, I just mean dual, taking the dual invertible sheaf of omega 1/2, and that's canonical isomorphic to Jm. Okay, canonical, when I say canonical, I mean up to a scalar in the base. Not up to mu2, up to a scalar. Okay, but then you can do other things to make it very, very much canonical. You can pick the constant. But so how do you, I'm not going to write the proof of this. I just wanted to give you a hint of how you would go about proving something like this, and also why it's not just, it's sort of the first result that you don't just prove by pure thought. There's some work that needs to get into this. And the fact is that you first use Stone von Neumann. You begin by using the Stone von Neumann theorem that says that both of these guys, so if you pretend that on a universal elliptic curve over a modular stack exists, both these guys should be irreducible representations of the Heisenberg group. And as such, they must differ by a line bundle. That's what Stone von Neumann gives you. So now the question is, so imagine having a line bundle that sits in between those isomorphism. Now you have to show that that line bundle is trivial. And that also depends on which base you're working. It might not be exactly. What you can show is that it kind of, what I show really in this proof is that that line bundle, it kind of comes from a line bundle over your base. So over schemes over Z, 1M, or whichever base you're working with, C, whatever. So whenever that's trivial, that line bundle is going to be trivial. So that's how you get your canonical. So when I say canonical, I mean that up to trivializing a trivial invertible sheaf. And that's, you get this isomorphism. Now, why do I put so much emphasis on this theorem is because that's your, it really gives you the transformation law of theta functions in a purely algebraic way. Right? How does that come about? Now, remember, you have this theta null vector, which you can define a purely algebraic way. I just wrote it as a Q series to remind you the origins of it. But really, theta null is completely algebraic geometric object that lives in the dual of JM. Now, by the theorem that I just proved, I call it algebraic Eichler-Zagier because it kind of, over the analytic base, it really comes down to the Eichler-Zagier theorem comparing Jacobi forms to vector valued modular forms. That's the name that I use for it. But anyway, this version works for over essentially any reasonable base scheme. And well, you get by dualizing, you get this isomorphism. And what that tells you is, so between your JM dual and between the sort of this dual of the Weil representation and half integral weight, the modular forms of half integral weight. So now you can view theta null not just on the right-hand side, but as a vector on the left-hand side. And as a vector on the left-hand side, it's completely clear what the transformation law should be, especially the half integral weight automorphic factor. How does that come about? It comes out because of this isomorphism. So there's a way of saying that theta, this vector of theta constants, is a modular form of weight 1/2 with values in a certain representation space. It's a completely algebraic way of stating a fact that it looked like it's analytic. Okay, so we go until 5:30, or there's some time for questions. So there is some additional results that I wanted to get time to detail, but remember that the vector, so the Weil representation should be whatever vector bundle you get out of that should be a local system. So you can show that. You can prove that purely algebraically. You can show that it trivializes. The WM trivializes over a finite Hall cover of your gerb KM, your metaplectic stack kappa M. So you can show that. That kind of use. I mean, it's sort of, you really have to dig a little bit into the details of the Weil representation, but you can show that. You can define Q expansions of vector value modular forms. And now I say WM, but really perhaps we're more interested in WM star, but just put a star there if you like. And that's what Showa was asking earlier. How do you, the question is, if you pull back, of course, there's this map that comes from the take curve, this classifying map to the modular stack. You can pull back vector value modular forms under it, but then how do you trivialize? How do you find the analog of omega can? And you have to work a little bit, but that's nothing really groundbreaking. Just has to do with how the theory of theta structures of Mumford. You can work with that over the take curve and find canonical trivializations. And you can define Q expansions for vector valued modular forms. Perhaps a bit more delicate issue is how do you, what is a holomorphic? What is a holomorphic vector valued modular form? And that you really kind of have to go back to the complex-analytic literature and see how that's done, because there's many ways of doing it. There's no canonical way of just extending something at the cusp at infinity. So you go back and see exactly how they did it, and it turns out that, well, I'll just talk about that, but what happens is that because of this WM, what you can do, you can break it down into line bundles over an appropriate final cover. And what you do, you really want to extend these vector value modular forms along these line bundles. So you kind of extend, I like to call it to extend these vector value modular forms along these line bundles of theta functions. I won't have too much time to get into that, but it's a beautiful sort of extension. It's very non-trivial extension, because you don't just get, so you'd be tempted to say, oh, a holomorphic vector value modular form should be just something that has expansion in the power series ring. You'll be tempted to say that, kind of like in the usual case, in the integral weight case. But that doesn't happen for these vector value modular forms. To recover the modular forms of receiver to do something else, because their Q expansion doesn't quite look like just by being in the power series. It is, but there's more to that. There's some kind of divisor happening at infinity. Now, once I do that, okay, well, there is a statement about dimension. If you work over an algebraically closed field and you have to exclude some characteristics, I can actually compute the dimension. These are going to be finite dimensional vector spaces, and I can compute the dimension of that using Riemann-Roch for the Mumford stacks. And I get different formulas, but different looking formulas than the usual ones, but they give you the same values, thankfully. So I've checked all the numbers, and I mean everything works out. I get the same exact dimension formulas that you get over C, but from a different point of view. Now, something else you can do, you can start from theta 2, 0, which is our first theta function. That will define, over a finite cover, it's going to define a line bundle, which is a subbundle Wn. Starting from the line bundle, you can define a purely algebraic theory of modular forms of half-integral weight. This time is in the pure sense, in the sense that we use in number theory. So the ones that behave like that theta function over there. So you can just do that. It's kind of like a spin-off of this construction. It was the original motivation, but now it kind of just turned into a spin-off of what you can do. And of course, you can compute dimensions. There's nothing surprising there. Okay, that's something that I can do. What other things you could extend this kind of, you can do several things with this theory. The low-hanging fruits here are to extend the theory to theta functions in any quadratic form. Essentially, the work that I've been doing, you just have to slightly generalize. That thanks to Mumford also, that is working such great generality that we can just take a lot of that from him. And that will put you, I think, once you do that, then it will also be clear, for example, the relation to classical modular forms, because you can take on unimodular lattices, and that will give you relationships with level 1 modular forms. Also, I think it might be a little clearer how the Shimura lift fits into this picture. The Shimura lifting modular forms of half-integral weight into integral weight. And I put Borcher's products there, but I'm not really sure exactly. I mean, eventually, it would be nice to understand a theory of Borcher's lifts in this algebraic way, though that's very far. Another direction, which I found very appealing, would be to construct like Ecke operators and try to construct motives and functions attached to these vector-valued modular forms. And also, you can go in the other direction and try to construct p-adic vector-valued modular forms, just like following the ideas of Professor Katz on the classical integral weight case. You can try and do that using some rigid analytic technique and do p-adic vector-valued modular forms, p-adic theta functions, and things like that. These are all directions that I've been thinking about. But yeah, well, thank you for your patience.